number one, okay? Number one says a spring has a spring constant of 310 newtons per meter. We are going to plot the potential energy for the spring when it is stretched by 1 centimeter, 2 centimeters, 3 centimeters, and 4 centimeters, and draw a curve that goes through the plotted points. The reason we're doing this is just because I want you guys to see how it gets graphed. You're not going to have to do a graph on your test. Okay? I just want you guys to at least be able to see what it would look like because we haven't done any graphs yet, okay? So, what is our spring constant that we're given?
310 newton meters.
310 newtons per meters. Okay, and what are the distances we're given?
1, 2, 3, and 4 centimeters.
So we have 1 centimeter, 2 centimeters, 3 centimeters. Or what should those be in though?
Meters.
Okay, so somebody tell me what those are in meters. 0.01.
0.02, 0.03, and 0.04.
Perfect. Woo, meters and 0.04 meters. Okay, what is our equation for the potential energy of a spring?
1/2 kx squared.
Ooh, yes. Oh, I'm so proud. Okay, so how are we going to find the potential energy for each of these situations? 1/2 times 310 newtons per meters times whatever the distance is squared, right? Okay, so you guys start finding those for me. 0.0155? What are the units? What are the units for potential energy, you guys? Joules.
Oh.
It's energy. Energy is always joules. You said 0.062?
Yep.
Everybody agree with Trunks?
Yes.
Awesome.
Yeah.
Does anybody have it for 3?
0.1395.
Does anybody have it for 4?
0.24 or 25.
Okay, cool. So thankfully, this is all the information we need for this graph, okay? Now, if later on this year or later on in your life, you need to graph something like this, we have an X and a Y axis all the time, right? Okay, so energy, our potential energy, is going to be what goes on the Y axis, and our distance is what's going to go on the X. So we'll have potential energy in joules on the Y and distance in meters on the X. All I'm doing is just drawing the picture. I'm not doing anything else yet. And I just put a 0 because the origin's always 0, right?
Right.
Okay, so don't worry. I'll pause right here while you guys draw your little thing. We're going to talk about how to determine that. Because a lot of people I've noticed struggle with that from last period. It took them forever to figure out everything. So we're going to go over it because I ended up showing them. Okay, so I'm going to decide that I just want to do like 4 little things, right? Okay, because I mean, we have 4 distances, right? And isn't the easiest increment of distances going to be by 0.01 each time? Okay, so our first one is going to be 0.01, then 0.02, then 0.03, and then finally 0.04, which makes our life really easy because those are our only distances, right? Okay, now, how I would go about determining how much to increment this by, okay, is I would say 0.25 minus 0.0155, and then divide that entire thing by 4. Because I'm taking my biggest number, subtracting my smallest number from it, and then dividing that by 4 to get about how much I should increment each one. 0.06? Okay, so see how this works out, you guys, watch. So that means that this first one is going to be 0.06. If you add 0.06 to this, what do you get for the second one? Yeah, what do you get for the next one? And then what do you get for the next one? Okay, so that means that this one is good enough. It just means on our last point, we're going to have to go a little bit above it, okay? But do you guys see how that gave us a pretty good idea of how to increment them? Okay, so you do the biggest number minus the smallest number divided by how many points you want to use. So if I had said I wanted 5 points, what would it be divided by? 5. Okay, good job. So now we need to sort of fill this in, okay? So we're going to come to the 0.01, and it's at 0.01, right? So it's going to be pretty far down here, okay? Then for the 0.02, since it's 0.062, we're just going to be a little bit above that first mark. And then for the 0.03, where do you think we'll be around? Above the 1, 2, but below the 18. So you can sort of guesstimate in there since there's not an actual grid drawn up here about where it would be. And then where would the 0.04 meter be? Yeah, it's going to be a little bit off the graph in this situation. And then it says to draw a line connecting them, okay? Now, I have a question for you guys. Have you ever heard when your math teacher shows you how to draw a graph forcing the origin? No? Okay, so what that means is that you'll see if we connect these dots, they connect fine, right? We got them connected, but they sort of just float over here. It doesn't go anywhere. So forcing a 0 would mean that I drop my pen, and then the dropping the pen is a very important part, you guys. And then we're going to take this over here, and we're going to make it go through the 0. Now, the reason we can force a 0 here, okay, is because what would happen if we did 1/2 times 3/10 times 0? It'd be 0. So isn't this technically a real point?
Yes.
So this is okay?
Yes.
Yes. So like I said, I just wanted to show you guys how we would graph potential energy, okay? If it was kinetic energy, we'd be able to do the same sort of thing. We just probably wouldn't have distance on the bottom because it really doesn't depend on distance, does it? What does it depend on? What does kinetic energy depend on, you guys? What does it depend on? Think about the equation. What's the equation for kinetic?
Mass. Velocity.
Velocity. It depends on velocity. Okay. So I want you guys to go ahead and start looking at number 3 while I erase this. So when I read it off, we can go ahead and start talking about our knowns. All right. Number 3 says that the human brain uses about 22 watts of power under normal conditions, though more power may be required during an exam, like you have next week. How long can one Snickers bar of 280 calories power the normally functioning brain? Okay, so let's think about this. What is the power that we're given? Okay, what else are we given? What's that?
280.
No, but like, what is that representing?
Or energy.
Energy. I'll say energy S, energy of a Snicker bar. Okay, so do we want energies in calories? What do we want it in? Joules. So who can see in their old problem set or notes how many joules are in 1 calorie? Nope.
Oh, how many? 4,186.
4,186 joules. That was on one of your guys' previous problem sets, okay? So who can tell me how much energy 1 Snickers bar is going to give you?
That's a big number.
Yeah, it should be a big number.
1,100,000.
Can you give it to me in scientific notation?
Oh,
It's
One
times. I don't know.
Is it 1.17 times 10 to the? Hold on.
Okay, let's do a quick briefing on how we do this. Let's say we have 200,000, okay? 1, 2, 3, 4, 5. So that would be 2 times 10 to the 5.
Is that negative or positive?
That's positive. It would be negative if we had
So it's 10 to the 6.
something like this. Then we'd go 1, 2, 3, 4, 5, 6, and that'd be 2 times 10 to the negative 6.
Okay, so it's 1.17 times 10 to the 6.
Times 10 to the 6. You guys all agree with that?
Mm-hmm.
What are the units on it? Joules. Awesome. All right, and we want to know how long can that power the normally functioning brain. So what are we looking for? Yeah, we're looking for a time, okay? Now, since you mentioned work, you guys, what did we say on our last candy bar problem that work was? It's the energy, right? Because all work is the change in energy. So you get given this energy by the candy bar, and then you change it, right? So it's the change in energy, okay? So what's the equation for power? It's power equals what divided by what?
W/T.
Perfect. How do we rearrange this for the time?
Multiply W by.
Wait, what?
You gotta multiply the T first. And
Okay.
then you have to
Wait,
divide by the P.
Wait.
Yeah, then you divide by the P. Yeah. Mm-hmm.
I got one.
Yes, that's correct.
That is correct because you can't divide by the W.
That's correct.
Yeah, you can't divide by the P. Yeah, you can't.
Okay, so you guys, what we did, okay, this is what we started with, right? And we want T by itself. So what they told me to do was multiply both sides times T, which moves that T over there. And then you want to get the T by itself. So if you divide both sides by P, you get that T is equal to work over power. You guys should be really familiar with this from when we were doing velocity and acceleration and all that stuff at the very beginning of the year. This is how we had to rearrange the equation all the time. Okay, so does everybody see how this happened? Yeah, you sure? Okay, so we're going to take this work of 1.17 times 10 to the 6 joules and divide it by that power we were given of 22 watts. So what does that give us as the time?
53,276.36.
So did you say 52,000 what?
276.
276?
Or yeah, 53,000.
Oh, okay. Sorry, I have a really hard time hearing you guys. You talk really fast.
I got 5.18.
Yes.
Point what?
36. I got.
Okay, now listen very closely to me, okay? If you have differing answers, it's probably that some of you typed in this and others of you used that full number, okay? That's the difference. Some people typed in this, some people just did answer divided by 22, okay?
Wait, so what's the
Because
difference?
No. It doesn't. Okay, so do you guys understand what I'm saying? Yeah, you promise?
So we put both answers were still right.
Why would you put both?
I'm talking about like,
Huh?
wait, I put it in the calculator like this and I got a different answer. That's how I did mine.
I think she's saying if we put one of the answers, are you gonna mark one of them wrong?
No, not to mention also on your test, it's multiple choice, isn't it?
Oh.
As long as it's close to whatever.
But I just want somebody to tell me what this is in hours.
Oh.
Oh. An hour.
48 hours and
Oh, yeah, you
14.8.
So, eat a Snickers bar and then study 14.8 hours for my test. One Snickers bar can power all of that work.
But in real life, doesn't that energy go to other things as well?
No, it's all going to my test.
Miss Bernal.
It definitely doesn't go to other parts of your body. What?
Find the hours.
How do you find the hours? Rose, watch. There are 60 seconds in 1 minute, and then in 1 hour and 60 minutes. Minutes cancel, seconds cancel, you get left with hours. Dimensional analysis. You guys should have learned that in chemistry. Chemistry. If you don't know it, your chemistry teachers failed you.
Yeah, I'm just thinking.
All right, no name and names here. Okay, number 5, you guys. You push a 67 kilogram box across the floor where the coefficient of kinetic friction is 0.55. The force you exert is horizontal. How much power is needed to push the box at a speed of 0.5 meters per second?
Well, the mass is 67 kilograms.
You're right about that. We have a mass at 67 kilograms. What else do we have?
A velocity of 150 meters per second.
Friction. Kinetic friction of 1.
Is it the kinetic friction or is it the coefficient of kinetic friction?
Coefficient of kinetic.
Okay, and what's that equal to?
0.55.
Do you have anything else? No?
That's a whoa.
Okay, what are we looking for?
Let's see.
How much power?
How much power?
So we're looking for how many watts. What's what? This is the coefficient of kinetic friction. It's mu k. Okay, so something else, since you guys can't remember what that is. Does anybody remember what friction is? Friction is, yeah, it's fun, right?
Yeah.
Okay, so let's solve for this force of friction. We're gonna put in the coefficient of kinetic friction. And what is normal force? How do we find that?
Mass.
Oh,
yeah,
yeah,
mass times
Yeah, mass times the acceleration due to gravity, right, you guys?
Mm-hmm.
So what's our mass? And what's our acceleration due to gravity? Okay, so somebody tell me what force you get. What? Does everybody agree with that?
Okay, it's 331.13.
I got 361.13.
I got 361.13.
Those are all the answers I've been told.
Yeah, it's 3.
It's 361.13.
361.
Is it the last one? Okay.
0.13.
Okay, so that's just our force of friction though, okay? So I want you guys to think about something. What is our equation for power? What does power equal? What else does it equal though?
Oh, F.
Force.
Yeah, FV. Good job. Do you know what that stands for?
Force times velocity.
Velocity.
Force times velocity. Okay, well we have a velocity, right? Do you think this is our force?
Yeah.
No.
Let me show you why it is, okay? So, let's say that this is our mass, all right? And it says we're pushing it horizontally, right? Which means we're applying some force, but we also then have friction acting against it, okay? Does it at any point say that the mass is accelerating? No. So if the mass is not accelerating, doesn't that mean that if we summed these two forces, they would equal 0?
Yeah.
So that means that this force and this force are the same, right?
Mhm.
So that means that that's the only force we're concerned about because that's the only force that's getting applied.
Is there one on this one?
Who knows? There might be. You guys have been doing friction for a long time.
Do you want us to solve that?
Yeah, so the question now is what is our power? So we're going to take 361.3 newtons times 0.5. What do we get?
180.27.
180 point what?
57.
What are the units? Watts. This would actually be a really good kind of question to put on your test since you asked.
Oh, Lord. I Check. Okay, sorry.
Oh, trust me, the test is already made. Okay, do you guys have any questions about this one? No? Okay, that was number 5. So we'll be moving on to number 7. How's your guys' day going? Oh, that's great. So happy to hear that. All right, number 7. A small airplane tows a glider at constant speed and altitude. If the plane does 200,000 joules of work to tow the glider 145 meters and the tension in the rope is 2,560, what is the angle between the tow rope and the horizontal? So let's think about this. What are we given? Okay, what is the work?
300,000.
Yeah, you can.
I'm about to put that in.
Okay, what else do we have?
The distance.
Okay, what's the distance?
145 meters.
What else do we have? Okay,
2,500.
you said 2,560 newtons. Is there anything else we're given?
What's the angle?
Well, that's what we're asked to find. Were we given anything else to get us there? No. Okay, also, since some of you guys are saying you want to do this in scientific notation, what would this be in scientific notation?
2 times 10 to the 50.
2 times 10 to the what? Okay, and so everybody sees that. 1, 2, 3, 4, 5. Woo. All righty. So how the heck are we going to find the angle?
We also got time for
No, we have a force. Let me draw a free body diagram for you guys so you can see. What do you think is acting on the glider?
Gravity.
What else?
Normal.
Yeah, normal if it's bringing it along on the ground. What else?
Tension.
And the tension is what we have at an angle. We're trying to find theta. You guys have an equation that will make this so easy.
Yeah. We should.
Oh, it's cosine, right?
What about cosine?
It's like cosine.
I'm not going to just put it up here for you. You guys tell me what it is.
Work equals force.
Is it force? This is cosine theta.
Yes,
Cosine.
it is. It definitely is. Okay, so question. We need to start rearranging this to solve for theta. What's the first thing we should probably do?
Divide by FD.
Yeah, divide by the force and distance to get that's equal to cosine of theta. Now what do we do?
You gotta do.
Who said inverse?
Oh
Inverse, okay? To get this theta alone, we're going to say inverse cosine of work over force times distance. Okay? So that means when we plug it in, we're going to have the inverse cosine of 2.0 times 10 to the 5 joules divided by our force of 2,560 newtons times our distance of 145 meters. So when we do that, what do we get as our theta? 57.39?
It'd be
You can round it
57.4.
to 57.4.
Yeah, I don't care. You can round it, that's fine. Okay, do you guys have any questions about that one?
We're still writing it.
I'm sorry, I was doing it as you guys told me to do it. Get mad at your classmates.
Slow down.
I think very fast.
I just wrote it as you told me to. That's all I did.
That was good. Well, you were fast. Yes, I did. Perfect.
Okay, we'll wait 8 degrees.
Yeah. That's why I have a degree symbol there.
Next is number 9.
Yeah, but your classmates still aren't done writing yet. I think you're one of the people they don't like for going too fast.
Yeah, no, you weren't. Yeah, too. I just think fast. It's not my.
Am I allowed to erase this yet?
I've been sharpening. I can.
All right, flip over to number 9. Okay, so number 9 says a particle moves without friction. So that's awesome, right?
Yes.
Okay. At point A, the particle has a kinetic energy of 12 joules. At point B, the particle is momentarily at rest, and the potential energy of the system is 25 joules. At point C, the potential energy of the system is 5 joules. We want to know the potential energy of the system when the particle is at point A and the kinetic energy at part C. Now, reading that, what do you guys think? How does that make you feel?
It makes me feel like crud.
Makes you feel like crud? Okay. Well, listen to this. This is the same particle, right? That's moving?
Right.
Okay. Can energy be created or destroyed? What is it? It's conserved, right?
Yeah.
We're conserving energy, or we're transferring it between potential and kinetic, okay? So that means that however much total energy we have at point A is the same amount we have at point B and the same amount we have at point C, which means, you guys, that we can say, you guys know how we've been doing potential energy plus kinetic energy initial is equal to potential energy plus kinetic energy final?
Mm-hmm.
It's the same thing. We're going to do potential energy at A plus kinetic energy at A is equal to the potential energy at B plus the kinetic energy at B, which is also equal to the potential energy at C plus the kinetic energy at C.
Yeah, that made
Yeah,
sense.
definitely.
I get it.
It means that at each point, the particle at point A has the same amount that it has at point B and the same amount that it has at point C. No matter what, the energy is going to be the same. It has to be. And they give you exactly what the energy has to be. Where do they give it to you?
Because you're at rest, the potential energy is 25.
Yeah. So when at point B, it says you're momentarily at rest. When you're momentarily at rest, what is your kinetic energy? 0. And what does it say your potential energy is there?
25.
25. That means that no matter where you are at A, B, or C, when you sum the potential and kinetic energy, it has to equal 25. Well, let me show you. So that means that this is equal to 25 joules, and it means that this is equal to 25 joules. Yes, but if I just say yes to you, then other people are going to get confused, okay?
But I'm proud about it.
That's good. I'm proud of you. What's the one value we're given in part A? But what is that for?
Kinetic.
Okay, so we're told that kinetic energy in part A is 12 joules. So how do we find the potential energy? Subtract. Okay, so what is our potential energy? All right, what are we given here? Potential or kinetic? Which one are we given? Read your paper. Yeah, but other people were looking at me like they didn't know what I was talking about. Potential. You're given potential. You guys, it's on your paper, okay? So what is our kinetic? 20. Was that really as bad as you thought it was going to be in the beginning?
I think we should go to the events out.
No. All right, do you guys have any questions about this one? No? All right, we're going to do 11 then. And then, like I said, tomorrow we'll do 13 and 15, so you guys are in the same place as everybody else. Yeah, you guys are going to have a lot of time. Because the other class, I think, took a little bit longer. Plus, you guys have a long class period. Okay, so number 11. It says, at what rate must you lift a 3.6 kilogram container of milk if the power output of your arms is to be 22 watts. So what are we given here? Okay, what are we told the mass is? Okay, what else are we given?
The distance, or yeah.
What are we given? I heard power and distance. What are we given?
Power is
Sorry, I'm looking at
22.
I was looking at power is 22 watts.
And distance is 1 meter.
Okay, we're not on there though, are we? That's part B. We're not there. So we're only looking at part A. Are we given anything else? What are we asked to find? So when you hear the rate, are you guys sure it's time?
No, it's velocity.
It's velocity. When you see or hear rate, your mind should immediately flip on to velocity. Immediately, okay? Rate is going to be velocity. Okay, so how are we going to find velocity? What's our equation? How do we get velocity alone? Okay, how do we get force?
Mass times
acceleration.
Okay, so what's the force then?
Should be 35.28.
What he said.
Well, no, hold on. We'll give you guys a chance to catch up with them. Okay, you guys got the same thing as trunks, so what are the units?
Units.
Okay, and so what's our power?
22.
So we're going to do 22 divided by what?
35.
35.28. So somebody, okay, I've heard one answer, but I want to wait to let other people catch up.
Oh, were you at 35 from?
Doing mass times G,
Oh,
like we.
But she said, I got points.
I got 26.
Okay, that's what everybody has said. What are the units?
Meters per second.
Ooh. Okay, that was part A. Now, Trunks, what's the distance we're given in part B?
1 meter.
1 meter. Okay, what are we asked to find in part B?
How long does it take?
Okay, so that's going to be time when we say how long does it take. Okay, how are we going to find time? Power equals what over time? Okay, so what do we need to do?
Okay, you gotta
First, you gotta rearrange it to solve the time.
You gotta multiply time it works.
Yeah, and then you're gonna divide by power.
Okay, so we have the time is work over power. So what do we need to find?
Work.
How do we find work?
Mass times acceleration, or 9.8 times distance.
Yeah, so we're going to do mass times acceleration due to gravity times the distance.
Oh.
Because the mg is force, you guys. That's how we find force. You've already found it right here. So you're going to take that, multiply it by the distance. What does that give you? That's mental math, you guys. You're multiplying it by 1.
28.
What are the units? Okay, so now what do we do to find time? Yep, we're going to take that and we're going to divide it by power. What's our power?
22.
Okay, so what does that give us? Do you guys agree with 1.6?
Yes. Oh, wait.